Yeah, hello everybody. Welcome to our webinar Innovations in Fusion. My name is Rainer Schramm, and I would like to present you today the way how we further develop the fusion technology. So I will talk about fusion, what is fusion in general, so that everybody knows the basics. I will discuss our furnace concept and what are our ideas to develop this further. Of course, I will take a few examples in Fusion so that everybody understands the basics and which parameters are important for a successful fuse speed. I will discuss, beside the classical oxidic samples, volatile components, fusion of reduced components, fusion of other techniques like ICP or ion chromatography, so that you just see what other techniques can also benefit from such a fusion technology. And of course, in the end, we will do a quick conclusion. If you have any questions, you can just put them into the answers and questions sector or chat sector. And at the end of this webinar, I'm happy to answer your questions. So let us start with the basics. So sample preparation for XRF. Just a little overview. So we could prepare our solids, for example, in such a sample cup as loose powder, or we measure in with XRF liquids in cups, or for example, we have direct a sample, a piece of metal, piece of plastic, we can directly analyze. We do some production control by analyzing materials, or to be more precise, we make a press pellet out of our powder. And last but not least, it's the fuse speed, which is then the highest level of a sample preparation for solids in XRF with the highest accuracy and highest precision, but of course also with the highest investment in time and money. But let's talk a bit more about fusion now. So to have a successful fusion, you need that your sample wants to build in such a borate structure. I mean, we have to think about that when we fuse our sample, we make a liquid. So it's a liquid glass. And of course, the most part of this material is our lithium borate. And the lithium borate in the glass will make such a loose structure. So there's not a real structure. It's just that the bindings will define the neighbors. And then in this arrangement, our elements from the sample have to integrate. And so we can imagine that all the cations will make a relationship to the oxygen, and of course the oxygen from our sample to the boron, and so on. Yeah, and only if the sample is willing to dissolve into that glass, only then we will have finally the chance to make a bead. And of course, we have a kind of an amorphous situation, and the sample should be fully oxidic. Otherwise, if we have reduced components like metal particles, they will never integrate into that glass, and then fusion will not happen. Yeah? You will just crystallize, or your glass will break down. So when we now have a fully oxidic material and we want to fuse it, the basic principle is always you mix your sample with the flux. Flux is the glass former, and nowadays we use lithium borates, mostly lithium tetraborate or some mixtures of metaborate and tetraborate. Then this mixture is heated up until it gets fully liquid. Then it's very important that we homogenize that. And when it's fully homogenized, we can pour it into a form, into a mold, and then we cool it down to get a glass. And then we can do our X-ray analysis. So this is the basic principle. And to heat, we can either use an induction furnace, or we use a muffle furnace, or we use a kind of a gas burner. We at FLUXANA, we concentrate on gas burners and muffle furnaces. Induction is not our specialty, especially because we would like also to analyze volatile elements and the fact that in induction, the crucible itself is the heat producer, and every crucible is handmade, so that means every crucible is a bit different. So the heat will be always, and the temperature always a bit different. And this has, of course, an impact to volatile elements. And so I think that in a muffle furnace and even in a gas furnace, you can have much more stable conditions to get this under control. So this is why we have decided to concentrate on these two techniques. So when we look on our FLUXANA equipments since 1996, gas fusion machines are in the market and very well known. And still today, there's really a fixed community who is further using gas, and there, in my opinion, is not a real argument against that. Gas fusion machines do a very good job, are easy to repair. Also, the price ratio of the beats are, in my opinion, lower than in electrical fusions. So there are quite a few arguments which support the gas machines. And nowadays we have electronic regulators which absolutely guarantee that the temperature is always the same. It's only the measurement of the temperature which makes some difficulties. And there we use an indirect measurement over the analytics that, for example, you take the sulfate in a cement and you just look how much sulfur you find in your analysis. And if it's a little bit too hot, of course, you lose more sulfur. If it's too cold, you lose less sulfur. And so very precisely, you can adjust your gas flows in the way that you hit the right sulfur value in the end, and from then on, it's just constant. The flames nowadays are a mixture of propane, oxygen, and compressed air. And the reason for this is that you want to be independent on your environment, so not depending on the daily air pressure and the temperature outside. So this combination and using oxygen additionally makes sure that you are absolutely independent on the environmental conditions. Then, of course, the agitating and the pouring is established over years. So we use really agitating, and this makes sure that you have a very efficient homogenization in your fusion process. And of course, nowadays, all kind of security features are integrated so that you can guarantee a safe operation. On the electrical side, we make them more than 10 years now. We use the lift bottom furnace design. That means the door is the bottom, and so we open it via a lift. And this means that we don't lose so much heat when we open the door. And our bottom is round, so this allows us also to have an efficient agitating mechanism like in the gas machine. We can achieve the same way to homogenize our samples, and in this way it's very efficient. And of course, we combine this with an autosampler so that you can automate your fusion so that one after the next sample can be fused. And in this way, you have a very efficient and cold-to-cold operation of your fusion process. Let's talk a bit about the furnace design. So like you see here, the furnace is round. We have the fusion room protected by a tube so that the heating elements are behind that tube and can never be spilled by the sample and flux. We have here this round bottom, which with a lift is just going into it. And here you can see also that the crucible are of course not in the center. So as more force we integrate, as better you can homogenize the sample flux into your crucible. Of course, everybody who knows muffle furnaces knows that inside a furnace you never have a homogeneous temperature distribution. And to guarantee this, in the moment we have more than one crucible in a furnace, we just turn this very slowly, like in a microwave, so that every crucible sees exactly the same heat. And in this way, we can guarantee that in this case, all four crucibles see exactly the same temperature over the fusion process. And when we make a high rotation, this in the next step, then of course with acceleration and stopping the rotation, the force moves the material inside the crucible in a way that you have a very efficient homogenization. So there was a comment here in the question and answers. There is a split opinions about fusion method. Others suggested that the samples are required to be calcined before fusion, meaning LOI free. Others suggest that no need for calcination, just mix the dried sample to the flux, then fuse as usual, which is the universal method and most accurate technique. I would say the most accurate technique is calcination because you exclude one parameter from the process. But this doesn't mean that you can't fuse non-calcined samples. It is just that then the LOI, the loss on ignition, is happening during your fusion process, and you have one parameter more, which can create an error. Yeah. So this is that means the more precise method is with calcination. Of course, the more flexible method is without. Yeah. So this is also give and take, I would say, between error and yeah, efficiency. Okay, let's go further in the presentation. We can, of course, analytically prove if the rotation and the homogenization is working. And this we can do with a sample. We just prepare 4 times. And then by experience, we know that silicon oxide is always the element the most critical or the most sensitive to homogenization. So that element needs to be very precise. Then you know that your agitation is working. And here we really set the speed very slow to see that it's not working. Yeah, and you see you have a very high error in the silicon oxide, very high standard deviation when we prepare 4 fusions from the same material. If I increase the speed now, then there will be the moment when then the standard deviation goes back to a normal value, and you see that silica gives very reproducible values. And this means this is a way to find out how quick you have to agitate to get really a homogeneous speed. And we made a bachelor thesis about that to find out for different materials, different speeds you need. And finally, we have defined nowadays an agitation speed which works for 99% of the materials, so that you're always on the safe side, that your fusion process gives homogeneous melts. Okay, let's talk about the throughput. We started with one sample in the furnace, and of course, then the autosampler is just exchanging it step by step. Then we built a machine with 4 samples in the furnace at once, which of course increases the throughput a lot. But because of the size, the furnace also is quite big, and the footprint of such a material is really big. Yeah, so this is a bit of drawback, so that we decided then to try out to use 2 samples in the furnace at once. And then, because the furnace is not much bigger than with one, the footprint is still very small, then you have a very efficient way of using your lab space. And so we decided for future machine design that we go for 2 per 1 furnace. And then when we combine this with, for example, 3 furnaces, we can do 6 sample completely simultaneous. Yeah, and this is how such a machine will look like. That means you have here 3 positions. That means inside we have 3 openings, 3 furnaces to handle 3 times 2 samples. Yeah? And the furnace will operate like until now at 1250 degrees, so that refractories or high quartz silicon oxide samples you can fuse without any problem, because at that temperature the viscosity is already so low that you still can mix the sample very efficiently. Then, of course, all the 3 furnaces are temperature controlled. We turn the sample slowly to make the homogeneous temperature distribution. We have the tube protecting the heating elements, and the furnace opens at the bottom so that we save heat. And you can also open them on the top so that in case you do reactions like fusion of ferroalloys, where you make an oxidation reaction, that the fumes can go out directly during that fusion step. After that, you will close it, and the normal fusion will then be done in the closed furnace. There's a glass window on top, so that you even have the possibility to observe your fusion directly inside the crucible. And of course, everything works 100% synchronous, so that it's reproducible. And here the inside design, so you have the tube with the heating elements around. And then, of course, every furnace has its own heating control, so that in the end, every of the 6 crucibles sees exactly the same temperature. But that's not all. We thought that everything we collected over the last 10 years in different ways to do fusion, we wanted to integrate in the same machine, so that, for example, the first thing is that we combine this with an automation. So you have here 6 positions, but in the same way you can load another 6. So that means when 6 are in the furnace, you load the next 6, and when the 6 are coming out of the furnace and will be placed on the cooling, the next 6 already go into the furnace. So in this way you have higher throughput, higher degree of automation, and you can do up to 12 samples then automatically. This is what I mentioned, and but of course now we can combine. That means that we have in the 2 back positions XRF, and we could then do ICP on the 2 front positions. Yeah, so then you're completely flexible. You can do XRF and ICP at the same time. You can also combine aluminum molds, which are used in a lot of industry for sulfide ores, together with platinum. That means here you could install 2 heating blades with aluminum molds, and in the back you can have the platinum molds. So again, you can do both at the same time. Or you want to do peroxide fusions for ICP or ion chromatography, you could load up to 4 peroxide fusion in one station. That means where you have 2 platinum, we do 4 peroxide crucibles, so that in total on one station you can do 8 peroxide fusions, fully automatic, then multiplied by 3 if you have a bigger machine. And last but not least, we could in the same way do 4 ICP crucibles on one rack, so in total 8. And again, this gives you a lot of flexibility in doing all your fusions in just one single machine for different methods in your laboratory. And last but not least, we have our quartz crucibles you can also use instead of platinum to do some trials, developments, application, special applications which normally will ruin your platinum crucibles. And this all can be done here with these kind of adapters. So back to fusion, to the recipes. So this I mentioned already in the beginning. This is a classical approach for oxidic samples. So you have something like 0.5 to 1 gram sample mixed with 8 gram flux, mostly lithium borates, and then you do the steps like mentioned here. In the moment you would like to do volatile elements, let me say with chlorine, fluorine, you can use lids in the instrument so that the loss is not so big. And this, of course, gives you then a much better precision and reproducibility. Also, for example, you're doing gypsum, you will see that you reduce the error significantly by using lids, and so that will just stabilize your application a lot. Here an example for that. For example, chloride in cement. You see very low level, but still in fuse speed, you can achieve a very stable value here, for example, in the NIST. And this is just what I said. Very constant temperature settings. The lid on the crucible guarantees you stable conditions inside the crucible, and in this way you can also run volatile elements. The most common are fluorine and chlorine, and of course also sulfates are for a certain degree volatile, but normally with stable temperature conditions, you always can do that very, very reproducible. Another kind of application is everything which is reduced. That means, for example, slags with metal particles inside, sulfide ores with the sulfur in form as sulfide, or carbides, metal powders, ferroalloys. So these are materials you need to oxidize first before you do your fusion process. Otherwise, there's a risk that your platinum will be attacked, and this you have to avoid, of course. And so there are different examples. Today, I would like to present you metal powders or black mass from battery recycling, where we take zero point 0.2 gram sample, add an oxidizer like strontium nitrate, flux, and a non-wetting agent. And then this is the sample, and oxidizer is always mixed first. This is placed on top of the flux. Then it is oxidized at a low temperature, let me say 600 degrees, for about 10 to 15 minutes. Then this is fully oxidic. After that, you increase then the temperature to the classical fusion at, for example, 1200 degrees. And then when it's liquid, you homogenize, you pour into the mold, and then you cool. That is the workflow. And this works very good because the critical step where you still have metal particles is oxidized at 600 degrees, where the platinum ware is still not attacked. Yeah, that's where everything is very safe. And only when this step is finished, then you go to a higher temperature to make sure that then the fusion process works nice. And here I give you an example from an NMC black mass. NMC means this comes from a car battery which has nickel, manganese, and cobalt inside. This is a kind of a carbon powder which is produced in recycling. And then you see how good such a fusion process can make the analysis of cobalt, manganese, and nickel, the main components. So we have here fantastic precision, repeatability in this sample preparation. This is just because we have this two-step oxidation and fusion process, where in both steps it's 100% guaranteed that it's really working straightforward. Now another completely different example, and this goes more to ICP and other methods. So I want to use my fusion system then to do either a borate fusion. That means a sample is fused with lithium metaborate, and after that poured into acid to get a solution, an acidic solution, which then can be used in ICP for analysis. Or the other way is I use peroxide fusion. For example, this is what we do with black mass together with sodium peroxide, carbonate, and hydroxide to fuse this completely on the alkaline side. And when you then dissolve this into water, so you place just this small crucible then into the water, and then the alkalines, the anions are leaking out. And you can do, for example, ion chromatography of anions. And this I want to show you here. So, for example, we analyze the fluorine in this black mass by this sodium peroxide, which is then dissolved into water. And this alkaline gives you exactly the fluorine value of your sample. When you don't let it alkaline. That means you add some acid. Then you can analyze the cations. And for example, with ICP, or I just also did it with ion chromatography. That means now I analyze the lithium in this liquid. And again, with ion chromatography, so get the lithium value out of my liquid solution. So here you see how flexible you can use this kind of technique nowadays. You can cover your XRF needs with classical platinum molds, with aluminum molds. You can use quartz crucibles. You could use also the ICP fusion also with lithium borate and acid, or with sodium peroxide and the water eluation. So there is a high flexibility which gives you a lot of possibilities to use such a system. Of course, the system exists in two versions, so you just can have 2 and 2 or 6 and 6. Yeah, so this is then just depending on how much throughput you need in your laboratory. And I think it's really a step forward to combine now all the experience we have made over the last 12 years in fusion in a small footprint, in a very flexible design. And of course, we kept everything what worked very well over the last 12 years. And like the agitation process, or like the way the autosampler handles the samples, that's all absolutely perfect and foolproof. Yeah, and we have also a certain degree of automation so that you can make out of 6 a 12 position machine, or out of 2 a 4 position machine. The flexibility I mentioned already, and of course, all the applications we know already and running in our laboratory, we have built into the software. So this is already there so that you can just start using it so you don't have a need to redevelop your fusion applications. And ICP I mentioned already. And of course, the future will be to combine these machines with robotics, so that you may even have more throughput and more flexibility and capacity in sample handling. Yeah, that was my presentation for innovations in fusion technology. I hope I could give you some new ideas how fusion will further develop, how you can improve the footprint of the fusion technology, how you can make a much more flexible machine you can use for all different kind of fusions you need to do in your laboratory, not only for XRF, also for other techniques. And I hope that one or the other point was important and interesting for you. So now I'm happy for some questions, and please write them into the chat or questions and answers, and I'm happy to give you then here some answers. So please write your questions inside. There is one coming. What do you mean with the fact that you would like to use sensor technology in future? Yeah, the sensor technology will have a big impact in, for example, maintenance of instruments. That means that you know already in advance when you have to clean your machine, when the furnace starts to break down and the heating is going over. So this can be all done with sensoric. So that means in the moment we include more and more sensors, we can help the user to plan more the long-term maintenance intervals he has to respect. And because the sensors are getting cheaper and cheaper and more available, and also software is more available, I'm expecting that in the near future this will have also an impact of such instrument developments. Okay, so the next question. How to calculate the final concentration of the sample when adding oxidizers potentially with loss on ignition, and gain on ignition? Does this play a role? Yeah, this is of course important because you need to get this information of LOI and GOI for your evaluation then in XRF. And mostly what we do is a trick that we use oxidizers which include heavy elements like strontium nitrate. And so let us assume we use 0.2, 0.3 gram sample and 1 gram strontium nitrate as an oxidizer. The strontium will become a very heavy absorber, and the matrix effects, and also this includes LOI and GOI, doesn't play a role anymore in analyzing a single element. So this helps us then in the end to just ignore these effects in their calibration and evaluation, and makes it also very robust. Yeah. And this is the trick how we just go around this LOI and GOI effect. There's another question. Can the 6 Plus system run with the furnaces at different temperature, for example, to perform an oxidation in one furnace while performing fusion in another? No, this is not possible. It's not possible because when you have 3 furnaces beside each other, they will influence each other. And this is the reason why you can only operate them on the same temperature. So if you really want to have that flexibility, it would be probably better to place 2 systems with 2 positions beside each other, and then you have 2 different furnaces completely separate from each other, and then you have this flexibility you need. This is how that works. So the next question. During calibration in XRF, shall we enter the LOI normalized value or the actual certified value? Yeah, this depends in the end in what state your sample was when you did the fusion. Yeah, because that means when you do the sample preparation and you fuse your sample, if it would be an uncalcined sample, then the LOI happens during the fusion, and then you have, of course, to include the LOI also in your calibration. This could be that you use alpha correction where you exclude the LOI, so that means automatically the LOI will be calculated, or when, of course, you are able to enter it, then you reduce the error of this calculation, and then you can give a very precise result. If you use calcined samples, then of course the LOI during fusion is always 0, and that means there's no need to enter it. Sometimes you will see programs where you still enter the LOI, but then this is only for calculations you do afterwards. That means you get your result from the calcite sample, and with entering the LOI, you just recalculate to the original sample. But this has nothing to do with the calibration process itself. So any more questions, please? There is nothing in the moment. I'm waiting a little bit. So perhaps there is more coming. Yes. Which element is not good when used in fusion? Of course, there are a few elements which do not work at all. I would say mercury, for example, is completely volatile. It will disappear. Other elements, selenium, also doesn't like glass. Chromium oxide, very difficult to fuse, makes always trouble, can be only handled in very high dilutions. So there are a few where fusion is limited, but most of the elements work very nice. Then there is someone who missed the beginning, but this is not a problem because you get the recording of that webinar, so don't worry. And the last question, I do not understand. When can I? Perhaps you can just repeat your last question because I do not understand it. Or you, of course, everybody of you can also send an email to us to ask questions also after the seminar. Okay, there is another question. Is LOI always CO2 in XRF software? In the real world, yes. But LOI means loss on ignition. That means everything you lose during your fusion. This could be also just carbon, in case you have carbon in your in your sample, like in the black mass from the graphite electrode, I have carbon inside, and if then I fuse this, the carbon burns away, and this is also LOI. So the CO2 is only valid for for samples which have carbonates, and of course then it makes sense. But LOI is more general and means everything you lose during fusion. Then here, is it possible to measure and fuse strontium oxide, chromium oxide, and zinc oxide in mineral? Yes, this is like in a cement sample, all three work very well. Um, Then the last question, is the Vitriox Electric available to buy now? It will be available in quarter 3. So from summer, the machine is really in the market. In the moment, it is working in the laboratory to make all the tests, to get everything really foolproof. And you know, our laboratory is the most critical customer. Only when they say the machine is now really doing all the tests and everything is fine, then we give it to the market. And this comes out very soon. Okay, any more questions here? Yeah, there's another one. Is LOI need to be included always as balance during calibration or as an auxiliary element? The LOI needs only to be included when it plays a role. And it would play a role when you use non-calcined samples, because then every sample will lose a different part, and the dilution in every single bead is different. And then, of course, the software has to know, yeah, what is the reason for that? And there are two ways. Either you define the LOI or you do it as balance, like you mentioned. Okay. There is another question. Should I treat negative LOI? So this means gain on ignition. Yeah, that means your sample gets more heavier during the fusion. A zero, some slack sample give us negative loss in ignition. That is correct. No, of course. And a gain on ignition means that your result in the end is more than 100%. Yeah, that is just a fact. And if you get then a sum of, let me say, 102 and 103%, this will be correct because some elements have taken oxygen from the air and included, and this is why your sample went over 100%. So this is really correct. You said that the costs are quite high with fusion. Is that related to the equipment needed? Um, yeah, okay. Costs high, we have to compare with what? Yeah, if you make just press pellets, you have to invest into a press and perhaps into a small mixer and into the chemicals like the binder. If you want to do fusion, of course, you can do it manually with a muffle furnace, but still you have to buy a muffle furnace, you have to buy the flux, and of course, you need some more time. That means the working time in fusion is longer. So this is where the costs really will differ. And when you invest into a fully automatic fusion system, it will definitely be higher cost than in a pressing system. Yeah. So that is why the costs will be higher. And this is what I mentioned. Okay, more questions. Should you mix the sample material and flux manually before putting it in the furnace? Or is the automatic agitation enough? No, I think it is better you mix it first so that every sample particle is surrounded by flux, because this is like when you put sugar into your tea, when you stir and when you make sure that the powder is not in one lump, it dissolves easier and quicker. Okay. Yeah, I'm very happy that you asked so many questions, because that means you're very interested in this technology, and I thank you so much for your feedback. And I hope that I could give you some more information about fusion technology. And when you have some more questions, just be free to send us an email, and we are willing to answer any further questions. Okay, thank you very much so far. And like I mentioned already, you will get the recordings afterwards. And so in this way, um, I would like to close this webinar now. And I hope I see you again in one of our next webinars, where we, for example, here on the 7th June, we talk more about automation. And this is more than in the automatic weighing of flux and sample in the laboratory for fusion. Okay, thank you very much. Have a nice day and see you soon.